Oh, I don't know if anyone's listening, but I'm going to wait about 5 minutes to let people trickle in. Oh, I don't know if listening, but also I meant to add that if, oh, there's people. Okay, so I don't know how all this is working. I'm broadcasting from a university connection, which ideally should be pretty good. You can always add in, if you type in the chat, group chat, I should be able to see it, I think. So if you have any questions, you can just go ahead and do that. Type them in there, and I'll try to get to them. If I don't, just put it in caps or something. Yeah, I'm going to wait a few minutes just to let people kind of trickle in. Since, yeah, things don't, well, at least in Berkeley, things don't start exactly on time anyway. They start 10 minutes late. Does anyone see the PDF? Does it work? Sorry, this is my first time using this, so I don't know. Ah, man, well, let me do that. Okay, so maybe you can't add it into the, but maybe into the Q&A? Nope, that doesn't work. Okay, well, I'm just gonna try this. If you guys have any questions, I guess, I think if you comment on the video, it gets put on the YouTube page, but then it should email me, and at least I should get that. Okay, so welcome to the second lecture in the BAHUG101 Introduction to Haskell course. So I wanted to mention that, again, this is just a, goes through someone else's course it's the CIS194 course at UPenn. And so those guys put together a fantastic curriculum, and I've asked them and they allowed me to use their material. So I've just kind of reformatted it into a presentation format instead of being the kind of notes that they had online. Yeah, if you have, all the stuff is there on that webpage. If you have any questions, there's also the Piazza page. Please feel free to ask any questions you have about homeworks or readings or anything about Haskell that you're interested in. We can go over that. So today, what we'll be talking about, if I get this to work, is a few things. First, we're going to talk about something called parametric polymorphism, which is basically functions that work for kind of any input type or any set of input types. Then we're also going to talk about what are total functions and what are partial functions. And then we're going to talk about common recursion patterns that we see in not just Haskell, but other languages. And then kind of like a functional programming style, or the Haskell functional programming style, how people usually write their code. And then at the end, we'll go down into currying and partial application. So let's start off with parametric polymorphism. So for parametric polymorphism, if you want a function to kind of take any input, you have to put what's called a type variable up in the type list here. So here is a function called length list that is, remember these two double colons mean type of. So length list is type of a list of A's, so whatever A is, and it gives you back an integer, right? And so in this case, I mean, it does what the name says. So the length of the list for an empty list is 0, and then otherwise, what we're doing here is that we say the length of the list is, so for a list that starts with one element and then contains all the other elements, which could be an empty list, we say 1 plus, and we recurse. So this function will work for any list, right? Because it doesn't really look at what's inside the list. It just says, okay, so there's an element here, I'm gonna count it, and I'm gonna move on. So it doesn't have to really care what's in there. So in Haskell, the caller of a function gets to determine the type when you're creating a polymorphic function. So you write the polymorphic function as is, and then the caller will determine what the actual instantiation of A is, what it actually is. It might be a list of ints, it might be a list of chars, it might be something else like that. The caller will figure that out, and then the compiler will just call that specific instance of your function, the kind of more specific one. So functions that are polymorphic but try to assume something on their inputs, some data type on their inputs, are not possible in Haskell, at least on the first order kind of view. So if we look at the following function called bogus, it's a function that goes from a list of A's to bool, and then the first pattern match there, it says bogus, I have the character X on as the head of the list with something else on the rest of the list is equal to true. And then the second one doesn't do a pattern match on char or anything. It's just basically otherwise. So in here, the first pattern match, what it's assuming is that the list of A is actually a list of char. So we can't do that. We need to be able to work for any list of A. So in Haskell, we can't actually write this function, at least not easily, because you have different pattern statement, you have different cases for different types. And however, if you have functions that kind of work for any of your types, then that's okay. So list is just very common because it's an easy one to have multiple functions defined for lists of something. So not empty is an easy function. It just says not empty is a function that goes from a list of A's to bool, and then if the not empty function has something at the head of the list, then you say it's not empty, and otherwise, if it is the empty list, you just say it's false. So this function is allowed because it doesn't actually try to match on the types inside. It just says, I know I have a list, and so I'm just going to do list operations, if that makes sense. So parametricity allows for what's called type erasure. So there's actually a good book on by Benjamin Pierce, I think, on programming language theory, but talks a little bit more about this. But basically, when you run the code or when you compile the code, the types are erased. So the runtime doesn't actually need any of the type information. All of it is included inside the, all of it is included prior to execution. So it's, yeah. There are, of course, like a lot of things, and Haskell's a general purpose language. There's ways to get around this as well, where types also carry through past compilation, but we won't talk about those for now. So Haskell has some kind of like funny things. So if I wanted to write a function called strange that goes from a value of type A to a value of type B for any A, for any type of A, and for any type B, can I write this function? And it turns out that I can't. The reason why is because basically I can't, there's no function that you could think of that would, for any input A, always give you a different type B. You would have to enumerate like every single like pair possible, and that just wouldn't be possible. You can define this function though, actually. So this presentation is a literate Haskell file, so you can run it. And strange is defined. It's just error is actually of type B. So here is it says string to A, but that's a little bit of it's just the way, that's how it comes up in the Haddock documentation. But so there's no way to write this function, and you would basically, yeah, you need it to work for any A and any B. The only exception is basically for if you write undefined or error. undefined kind of will take the place of any value, but when you try to actually execute undefined or error, it will just crash your program instead. And then also, one thing about parametricity is it kind of allows us to figure out a little bit about a function before we've actually looked at the code for it, which is kind of a neat property that we don't necessarily have in other languages. So here we have a function called limited that goes from type A to type A. And so what functions can we think of that go from type A to type A? Well, if you have a value of type A, well then there's the obvious one, which is you just return it back to yourself, right? So you do nothing to it. And it turns out that that's actually the only function you can write for going from A to A. And so based on the type signature, we know that the limited function, the definition of the limited function, the limited x equals x, that must be how it's defined, how that limited function is defined. And actually there's a cool, I don't know how to say it, degen I think it's actually on the IRC, Haskell IRC, I'm not quite sure though, but there's a Haskell package called degen that you give it a type signature and it's a general theorem prover, but it will actually try to find a function that will match that type signature. And in certain cases, there's only one, which is kind of crazy, and it will go find it for you, which is awesome. So now I want to go talk about partial functions and total functions. So this is a little bit different than the parametricity thing. So we'll be switching gears. So say I have a common function in Haskell is head. And people use it very often when they're learning Haskell. And what it does is it gives you back the head of the list. So here what we have is we have head takes a list of A and returns A. And we see in the pattern match that it takes the head of the list, gives it the name X, and just gives you X. But there arises a problem when you try to run head on the empty list. There's no pattern match for it. Actually, if you try to compile this code, besides it complaining that you would not necessarily have any capability to, that you would be missing some matches, it would also complain you had redefined the head function. But so this will just throw an error, because basically what happens is that you don't have that defined. It doesn't know what to do for that particular input. So it will throw an error. It cannot produce a value of type A. So in actual Haskell, head will look like this. It looks like a function of type A going to, of list of A going to A. And then if there is an element in the list, or if the list is longer than one element, it will take out the first element, and then otherwise it will actually just throw an error, kind of like what we had before. So this will just crash your program. And so this is what a partial function is. This is a function that does not define for all inputs of its, all values of its input type. So here, the input type is list of A, and is not defined for all list of A. It is specifically not defined for lists of A that are empty. So it will just instead crash. Yeah, sorry. So head is a partial function. Oh, there's a typo there in my markdown. So it is not defined for all inputs, and certain inputs will cause head to crash. In contrast, total functions are defined for any input, for all inputs of that type, all values of that type. So it is common practice in Haskell to avoid partial functions, and some common partial functions are the head function, which gives you the head of a list, the tail function, which gives you everything but the first element in the list. Oh yeah, the head of the list, the first element of the list. Sorry, that was kind of a recursive definition there. Recursive one. Init, I think that gives you everything but the last. I don't actually remember. I've never used that function. Last does something else with lists, and then the double bang, which is a operator. So it's in the parentheses there to mean that you can use it infix notation. That will just take you. That's basically indexing a list. So that will take out, say, if you say you have a list of 5 elements and you say that list double bang 4, it will take out the 5th element because it's 0 indexed. But so these functions are partial because there could be. So for example, with the double bang, if I wanted to take out, if I had a list of 5 and I asked for the 10th element, it can't find that. So instead what it will do is it will just error out on you. So it's not defined for every input on that int. It's only defined for inputs, integer inputs from 0 to 4 for the index. So here, so it's good to like avoid partial functions. So here's the function itself happens to be total, but it uses partial functions. So it's a bit kludgy. So we have this function called doStuff1 that has a type remember the double colon is type, of a list of integers and returns to you an integer. And for the empty list, it gives you 0. For the list of only one element, it does 0. And otherwise, what it will do is for a list, it will take the head of the list and add it to the second element of the list. I had to read that for a second. Hey, I did these kind of late last night. But a much better way to do this, because head is partial and tail is partial, so it's kind of like trying to figure out exactly what's going on here. We can make this simpler by pattern matching. So here what we do instead is that we say, okay, so these first two cases are the same. And what we're going to do is instead of taking the head of the list and then the head of the rest of the list, we're just going to actually pattern match on them and say we're going to take the first element and the second element and then ignore the rest of the list and then just add them together. So not only doesn't use any of those partial functions, it's also a lot easier to read. So now we're going to skip a little bit and go into recursion patterns. So what can we do? So we've been talking a lot about list of A, because list of A seems to be a very common thing to be operating on. Oftentimes, actually, in functional programming, you're dealing with lists. They're a very basic data structure. So if you have a function taking in a value of type A, what exactly can we do to it? Well, one thing we could do is we can do something to every element of the list. For example, we could take every element of a list and multiply it by 4. Another thing that we can do is keep only certain elements of a list. So a common thing for this would be like, say you have integers from 1 to 10, and you only want to keep the even integers or the prime integers or something. You can do that, or that's one thing you can do with a list of A. One thing you can do with a list of A is you can try to combine elements in order to make like one kind of combination of them, so some summary of the list. So for example, you can take the sum of a list or the product of a list. That is a way to combine all the elements of a list. And there's quite a few other things. So I guess maybe if you want, you can post on Piazza other things you can think of doing with just like a list of A, what other types of functions there would be. So let's try to do that first example. Let's try to do something to every element of the list. And what we're going to do is we're going to add the value 1 to every element. So we're just going to write a very simple function. It's going to be called add 1 to all. So it's a function that goes from a list of ints to list of ints. And add 1 to all for an empty list just does nothing. And then add 1 to all otherwise, pattern matches takes out the head of the list and says it adds 1 to it, and then appends it basically recurses on the rest of the list. So it will say for the first element of the list, it will add 1, and then for the second element of the list, it will add 1 to it and create a new list out of that. All right, so that's pretty simple. If we want to do another function that has a similar kind of concept, we can take the absolute value of every element of a list of integers. So here's a very similar function. The only difference here is that we're taking the absolute value of x instead of adding 1 to it. But notice how otherwise this base case, this empty list giving you an empty list, and the recursion call here, the abs all on the rest of the list, is very similar to this prior slide where we had add 1 to all on the rest of the list. So those are very similar cases, but they do quite different things. And then something else that's kind of a common tutorial is that you could square every element in an integer list. So here for an empty list, we're not going to do anything. And otherwise, we're going to square the first element and then keep recursing on the rest of the list using the square all function. So if we look at this, we notice that we see some sort of pattern. Oops, this should be a question mark. Sorry. So it seems like we keep doing the following. We keep basically writing this function where we have a question mark here, and we're going to fill that question mark with the function f, which does something to the value x, right? It does something to this head of this x, and then you keep going. So one way this isn't actually Haskell code. It doesn't compile, mostly because partially the question mark in there. But we can write this in actual Haskell code by making our function take in a function. So here we have, and you'll need the you'll need the parentheses for this. So here we have do something to each integer where we're taking in, so that this first part here is we're taking in a function that goes from integers to integers, and then we're taking in a list of integers, and finally returning a list of integers. So, and remember the underscore basically means that we're just going to ignore that. In that pattern match, we're just going to ignore that input. So here, when we get an empty list, we don't care what function we got. We're just going to return the empty list. And otherwise, what we're going to do, if we get some function and a list that starts with one element and contains the rest of the list, is we're going to apply that function f to the first element of the list, and then do something to each of the remaining. The note that, so the recursion call here changes slightly because I have to keep passing f back. It is in the definition of f, so I have to keep passing it through as it traverses the list. So it turns out that we can make this even more generic. So the prior one was on list functions that go from int to int on lists of int. So that was a lot of int. So the general function is called map. So map is a function that takes a function that goes from A to B and a list of A's and returns to you a list of B's. So it's exactly the same as before, but it's polymorphic. So it doesn't actually require that you have a list of integers or you have a list, or even that you have, so a lot of our cases where we took in a list of a certain type and returned a list of the same type. That's not required for map. But otherwise, it's the exact same thing. Empty returns empty. Otherwise, we apply f to the first element, and then we recurse on the rest of the list. So it's very common to, instead of writing the functions that we wrote, what we would write instead was we would write these. We would say add one to all. We would define it this way. We would say map, and then we would apply the map the +1 function over the list x of s. So people will say like mapping over something. And then for the absolute all, it's also a very similar definition. We just say map the absolute value function over the list of x's. And then the square all, we just map the square function over the list of x's. And so note here also that we have included these functions, basically the operators, the infix operators with one of the arguments already applied. And so this is actually a function that takes in one input and returns to you one output, instead of being a function of two inputs returning to you one output. Okay. So that was map. So that was kind of like doing something one to every element of the list. Now, what if we want to do filters? So if we want to filter a list, for example, if we want to keep only the positive numbers, positive integers in this case, we can write this function, keep only positive, which takes a list and returns a list. Could be potentially empty. But so if we would get an empty list, we return an empty list because we know we're not doing anything to it. And otherwise, this keep only positive, we're going to match on the first element of the list and the rest of the list, kind of a common pattern here. And then we're going to use guards. So what we're going to say is we're going to say, if the first element of the list is greater than 0, then we're going to keep that element, append and put it on the front of the rest of the list, where we keep recursing, stepping through the rest of the list. Otherwise, we're not actually going to do this append. We're just going to keep going. So we're not going to keep that element. You can do another function that's very similar that keeps only the even values, and it's defined, as you can see, very similarly. The base case is the same. Here, this function changes. Even x is different than the x is greater than 0, but otherwise, every part of it is the same with only name changes. So here again, we can see a kind of common pattern. So here what we see is that if we want to keep something, we have a function that goes from, we want to take in a function that goes from integer to bool. So that tells us if we want to keep that integer. We take in the list of integers and return a list of integers. So for the base case of an empty list, we just return the empty list. For a base case of, or for the case of a list having a first element and a rest of the list, we basically run this function p, which determines whether or not we should keep this element. And if we do want to keep this element, if it's true, then we do this append, cons. So we say x is cons onto the front of this list. This keeps something p of x of x, x of s. And then otherwise, we're going to basically not do this cons operator. We're not going to keep x at the front of the list. We're just going to do the rest of the function. And again, this can be simplified, as you can imagine, to be more generic by just saying we can take a list of any a and give us back a's as long as we take in a function that goes from a to bool. So this is exactly as before, but the function is called filter. So you'll see filter inside Haskell, inside the standard prelude. And here you might hear people sometimes call this p function called the predicate function. So it's basically just decides, it's binary, whether or not you put in a value and it tells you true or false. So that's basically what it is. So the final kind of things we could do to list of A was combining elements of list of A. So here I have, and so the single quotation at the end is just because these functions are already defined in Haskell. But I can sum the list. So if I have an empty list, then I just say the sum of it is 0. And then if I sum a list that has an element and the rest of the list, I'll say the first element plus the sum of the rest of the list. So that's, again, another recursive case. Another thing we could do is product. So here, this changes a little bit because the basic, if I multiplied by 0, basically what would happen here is, so eventually when you do these recursions, this product will be called on a list where the head is some element, x of s is the empty list, and then it will call this case. And if this was 0, it would just give you 0 for the entire product of the list, which wouldn't make any sense. So in this case, this what we'll call an identity element. The identity element for this function is 1. So, but it's otherwise very similar to the sum case. And then length is a similar case. So it takes a list of A and returns to you an integer. So here it doesn't return the same type as the same list type, and also it's polymorphic in the list type. So if I have a list that's empty, I'm going to return 0. It has no length. Otherwise, what I'm going to say is, okay, I don't really care about the first element because I'm just going to add 1 here, but I'm going to say 1 plus the length of the rest of the list until I reach this base case again, where I've reached an empty list, and I'll add 0 and combine them all together, or add them all together. So again, we see a kind of common pattern here. We match on the empty list, and then we have some base case value. And then here we match on the head of the list and the rest of the list, and then we have some binary operator in the middle combining the first element and the rest of the combination of the rest of the list. So the basic formula for this is basically combine. So here we have like a list of A's, and we return some value B. And B could be a list itself, but in this, the most base cases is you would combine down to a single value often. So here, if you combine with the empty list, you'll get some base value. So in the sum case, it was 0. In the product case, it was 1. And then when you actually have a list that has something in it, you basically say x, and then you combine it with some binary function with the rest of the list. So this is combine x of s. So this is called, in Haskell, called a fold. And there is a function, there's not actually a function called fold. It's called fold r, but we'll call it fold here for a second. So fold takes in a function that takes in 2 inputs. It's a binary function. It takes in an A and a B and returns to you another B. And then it takes in B. This is an initial value. So this is that like starter value we were talking about. It was either 0. It was 0 for the sum case and 1 for the product case. And then we take in a list of A's and return finally a B. So fold on an empty list will just give you that initial value that you put in, that you call the function with. When you try to fold with a list that is not empty, what it will do is it will apply that binary function on the first head of the list and the whole combined value of the rest of the list. So remember, when you're doing kind of recursion, one thing is oftentimes you're thinking a little bit backwards. So here you would say, like if your list was 1, 2, 3, 4, then this, and you were coming back up to your final case, you would have, say, plus, you would say 1 plus, and then this, which would be 2 plus, and then it would have another paren, and then 3 plus, and then finally 4 plus 0 would probably be your base case. And then it would go back and undo all those parens and combine everything together. So folds are a little tricky. If you have any trouble with them, I guess just let me know. There's also, I think it's just one of those things like with practice that you'll see it. Oftentimes, like you can think of these as in other languages, if you were doing a for loop and trying to combine all the elements, you are probably doing a fold. So we can do our prior examples by using the fold function instead. So sum becomes just a fold where we pass in our binary function is just plus, and our initial element is 0, or our identity element. For product, we're doing the multiplication binary operation or binary function, and then our identity or initial element is 1. And then for length, we're folding this add 1 function. So notice add 1 here, we've used a where clause, where we're saying add 1, we ignore whatever our first input is, and our second input we'll call s, and we say just 1 plus s. So here we're folding this function over our list with an initial value of 0. And we're basically just ignoring the values inside the list. Okay. So in Haskell, there's actually several different types of folds. So the one we just talked about was fold R, which folds, as people will say, from the right. So if you say have a fold R with some function, an initial value, and the list A, B, and C, it's equivalent to saying I'm going to say F is a plus just because it's easiest to talk about from level. You'd say like A plus, then comma, or paren, B plus, paren, C plus our initial value, and then paren, paren. There's another function called fold L, which folds to the left. So this one will take our initial value and then add it to the first element of the list, and then the second element, and then the third. And then there's also fold R1, which folds from the right eagerly. So these first two functions are lazy functions, which are the standard for Haskell. Fold R1 is a eager function, so it will not produce any thunks. It will not basically say, hey, like I'll only acquire values from fold as I need them. It will actually, when it gets called, will just evaluate all of fold, the entire fold without pausing at any intermediate values. And then fold L1 is similar to fold L, except for it also folds eagerly. So in general, fold L has poor performance, so you should try to use fold R or fold L1 instead. And if you want, we can talk about it on the forums, or you can try to figure out why particularly. It has to do with this being lazy and the way these parens are positioned versus this case that causes fold L to not work very well. And we actually haven't talked about infinite data structures, but for infinite data structures, you can often do a fold R on them, but you cannot do a fold L on them. You will run out of space before you reach the end of the list. So now let's talk about functional programming style, now that we've talked about a lot of different types of, I guess, functions inside Haskell that people commonly use, or patterns. So for this, it is common in Haskell to kind of glue functions together, and what you'll see what happens is that people use this dot function. So dot is actually called compose, so it's the compose combinator. What it is it takes in a function from B to C, and then a function from A to B, and basically what it does is that it just glues them back to back. So we'll take the value, that function G, which is the A to B function, it'll apply that to some input, grab the value that comes out, and then feed it into the first function, the B to C function. And then it gives you back, so there's no parens here. You could put parens here if you wanted to. It doesn't matter in this case. It gives you back a function from A to C. So it basically eliminates this B intermediate value that you're looking at here. It still gets calculated, of course, but it's just, you don't necessarily, like if you gave someone a function of just A to C, they can't tell if it went through this kind of intermediate B value. So if say we wanted to apply both an add one function and a multiply by 4 function to a list of ints, we can do that with a map, which we learned about before, applying one element to, or applying a function to each element of the list. And our function here is a little different. What it will do first is it will do the +1 function, right? And so we'll take our value in the list +1, take that value, and then feed it into the ×4. So if we had, say, 3, it would say 3 + 1, give us the value 4, feed the value 4 into 4 × 4, give us the value 16, and then continue on to the rest of the list. Another combinator that is often used, and there's more uses than this one, but the common one is kind of to remove parentheses. But so here we have a weird function. So this is a function that takes in a function from A to B and gives us back a function from A to B, which seems a bit silly, but this is exactly it. F, so this is just because it's infix, F $ of X is just F applied to X. So this function is often used to remove parentheses, and this is because of the way that operator and function precedence happens. So for example, oops, spelled wrong, maybe. Anyway, so if I want to negate the number, what am I doing? Negate num even 1. Negate. So I'm going to filter the list for even functions, then I'm going to take its length, and then I'm going to negate that value, because that's something I want to do very often. So this is a little bit weird because I'm kind of, well, I'm reading it from right to left anyway, which kind of happens in a lot of programming languages. But then I got a lot of these parens in here. So I can write this without writing any of the parens by including $signs, which is equivalent to like if I replace this $sign with a paren here and then a paren at the end of the list, at the end of the statement, it's the same. So now I can see I'm going to filter even x and then apply length and then apply negate. And then actually, what you probably more commonly see this in Haskell is as negate. This is final one. What you would do is you would say, actually, you would see it slightly differently, but you would say, okay, I'm going to take this x and I'm going to apply this function to it. So here I have a function where I've used my dot operator instead to make a bigger function and kind of throw out those intermediate values. So I'm going to first filter that x, then I'm going to take the length of it, and then so x is a list, and then I'm going to negate the final value from that. Then I'm going to take this entire function here, highlighted, and apply it to x. So often you will see this pattern often of something composed with something else, composed with something else, composed with blah, 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 blah. So a bunch of functions composed together, $sign, some input, or some sets of inputs. Another thing that you'll kind of see is that for very small functions, it gets a little bit weird to use where clauses or let clauses. So here, if I want to duplicate every element in a list, so if I have a list of strings and I return a list of strings and I'm duplicating it, I can map this duplicate function where I take each element of the list, which is itself a string, and I just say x, the string appended to itself. Excuse me. So in this case, it's a little weird, just because I have actually a lot more written. Like I have this where clause and all this stuff down here. Like I don't need to define this. I have a lot of text that's kind of, really I just want to say I want to do this, right? So Haskell allows you to have what's called lambda functions or anonymous functions. So here I'm going to map a function, and then so anonymous functions kind of start with this backslash. You say backslash and then variable. And so variables in lambda expressions would be variable space, variable space, variable space. And then you have an arrow. And then you define what that function is on those inputs. So here we are defining a function, a lambda expression that takes in a value x, a function that takes in x, and returns that x appended to itself, right? So here I don't need to use that where clause. It's a little bit simpler because the function is very simple in and of itself. So I can basically shorten this up a little bit. I would note that, so there are cases where you use lambda expressions besides the most trivial and small functions, but they're often best used for the smallest functions. Otherwise, if you have a larger functions, lambdas are a little bit confusing to read and can't really put a lot of documentation attached to it. And here in this case, if I wanted, for some reason, if I say wanted this duplicate function in somewhere else in my code, I can't use it because here it's contained in a where block, and here it's contained in a anonymous function. But if I instead made it its own function down here that just like down here, it said dupe is a function that takes in a list of A or a list of string and returns a list of, no, it takes in a string and returns a string, sorry. Then I could use it in any function that I wanted. And then finally, what we're going to talk about is currying and partial application. So this is kind of related to functional style. And also we'll answer a question you may or may not have had. So here, when we first talked about, so in the last lecture, and if you didn't catch the last lecture, you can read up online on the CIS194 page for their kind of lecture notes. So we talked about a function that takes multiple inputs as just being separated by these arrows here. But it's kind of weird, or at least when I first learned Haskell, I thought it was a little weird that I have like a integer here, and then why is this one not an output, and why is it not, like what's going on here? Like why, usually in a lot of programming languages like C or Python, I have like function name, paren, like all its inputs, and then I might have a return type like way on the, or if it does have return, if it does have types, I might have a return type before the function definition, or if it's like go after the function, like after the function declaration at the end of the line. But usually I would have something like that. And here, there's like no syntactic difference between the inputs and output. And there's a good reason for that, because it turns out that Haskell only has functions that take one input. Crazy. So all functions in Haskell only take one input. It's a little bit weird that way. But what happens is that actually you can look at this as a function that takes in an integer and returns to you a function that goes from integers to integers. So here, what I've read, so these two functions are the same, f and f prime. So f prime of x is equal to, and here I'm using a lambda expression. I'm saying I'm going to return to you f of x, f prime of x is defined as a function that takes in an input we'll call y. And then what it does to that is it takes 2 times that original x we got and adds y to it. So function application is also partly, so it's less associative, also to allow for this property. So if you call f of 3, 2, so our original function, what it will do is it will actually call f of 3 and return to you a function, right? Which that function here, the stuff that's in parentheses, it will then apply 2 to that function. So if you ever were curious, so you can basically, whenever you see, if you see, since it's right associative, if you ever see nested parens on the right side, those are not necessary. If you see them on the left side, they are necessary because that would be because of the way that this is right associative here. Yeah, and there's actually like, we could talk about it, well, maybe in a completely different course, but this is, the arrow is also a function, crazy. So, and it's defined in the prelude, or in the base, and you can go find it if you want. So currying is the concept of basically taking multiple argument functions and turning them into functions that take in a single argument and then probably return other functions. So one way, so in Haskell, if I want to go use the curry function, there's a function called curry, and we'll get to that. But I can pass in 2 values. I could do a kind of multiple input to a function by giving it a pair. And the pair itself is 1 value, but it contains 2 values inside of it. So we'll call it a multi-input function. So here's a function. This is the same thing as I had before. So when I'm adding primes, I'm usually not changing the definition or the way the function works. I'm just changing the way that it's implemented. So here I have a function taking in a pair where I pattern matched on x and y. And what I'm doing to that is I'm taking 2 times x and adding y, just like before. And then if I want to basically take functions that are in this f double prime form and turn them back into the functions that take in 1 input at a time, I can use this curry function. And if I want to go the other way, so here I have a function that goes from, it takes a normal 2 input function and then returns a value, and turns it into a function that takes in a pair of A and B and returns to me a C. So these functions, I don't see them super often. You will probably run into them if you're doing any of those. So what are called higher order functions, where higher order functions are functions that take in functions. So those include, as we've defined now, map, filter, fold, curry, uncurry, they take in functions. A lot of the other stuff we've talked about. It's very common in Haskell to write functions that take in other functions. So you might use this. There's a related concept to currying called partial application. So the idea is that since all Haskell functions really only take 1 input at a time, you can stop applying inputs at some point, and what you get is just the function that will eventually complete your computation. So here, if we have a function we've defined as add, so add takes in 2 values and returns x plus y. If I want to make a new function, add 4 of y, I can just say add 4 to y. Oops, I should have just said add 4. Yes, so this itself is a function, right? So this is an add 4 is a function that it's applied to y. So if you do this, it's called, so this part was kind of like partial application. You don't actually have to, it's equivalent to say add 4 as it is to say, like combined, add 4 as 1 word and add space 4. These are equivalent. But this only works for applying functions, applying values from left to right. So if you want to apply values in some other order, say a random order, you would have to use basically a common way to do this would be lambdas. So you would write a lambda that would just take the inputs and flip them around or only apply some of them, something like that. And so there's a little bit of an art in choosing kind of like, usually you want the far left input, like the first input to be the one that changes the least for you. And then the far right input to be the one that changes the most for you. So a example might be so say you have a database function, and you have a function that takes in a database itself, and then, or like a cursor, and then something to do with that cursor. If you're applying in the same database, we probably just want to use that. You probably just want to have like one cursor that you're using often. So what you'll say is you'll partially apply that database function to the cursor and come up with a function that will just say, for that database, do any other function that you want. And then, so this leads to what's called, so all of the above, everything we've done so far leads to kind of what people might call whole meal programming. So if you consider the following function, so it's got that lovely standard CS name foobar, which takes a list of integers and returns to you an integer, and it does literally something random. It isn't very Haskell-y because it's rather low level, where it's kind of, it's checking on things individually and kind of breaking things apart. You don't often see that a lot in the Haskell. So instead what you would do, you would probably see something like this. So you would see something where you would, so foobar prime, so remember the prime means that we have the same meaning but different implementation. So here what we're going to do, and because of the way the dot operator works, or just function application works, we'll be reading partially from right to left. So foobar is a function that first will filter your input with this function here, greater than 3. And then it will map this function, which is a times 7, and then it will add 2 to those elements that made it through the filter. And then it will finally take the sum of the whole list. So here, basically, instead of thinking of direct manipulations that you want to perform on some data, so up at, like in foobar prime, we're thinking about basically if we have a list, what functions are we going to apply in a kind of pipeline fashion? So here we're going to say like, our list goes through this pipeline, this part of the pipeline, and gets filtered down, and then it gets mapped over and finally reduced or summed up into a one number. So one thing actually so one thing that's kind of weird in Haskell is that, so here I haven't actually noticed this function, it takes in a list of integers, but I didn't give it any inputs. And that's because basically, since we have this pattern, if you ever see the pattern of like something dot some, or like functions composed together, then $, some value, or it's only one input, and your function is only one input, you can actually drop the $, and the X, and it just, Haskell can figure that out. Basically because we're just saying, oops, sorry about that, foobar is equal to this function here. So because this is a function itself with this type of list of integer to integer, and so foobar is this function. Okay, I think, yes. I ran out of slides. So that is all of the second lecture. For the homework, so the homework's obviously optional. It's pretty easy. So I encourage you to do it. It's online, and I'll post the link, but it's on that CIS194 page. It's the lecture 2 homework. And if you have any questions about the first homework or the second homework, post it on the Piazza page, please, and we will try to get back to you. I actually have 2 guys who are trying to help me in case you guys have any questions. Yeah, and then also associated with that is if you go to the same CIS194 page, they'll have like recommended reading. So I don't think this week has any recommended reading, but if you want to read any books to try to catch up, there's the Learn You a Haskell for Great Good is a good book. It's in the name. And there's also Real World Haskell. So they're both a little old, and especially the Real World Haskell one has been like, there are some things that are a little outdated in it now. And then also the Learn You a Haskell for Great Good doesn't have problem sets, but we have problem sets, so it's okay. But yeah, so those are the best books I would know off the top of my head for kind of this type of course and reading on the side. So I would highly encourage you to read. If you find anything online that you think is great, please post it as well. I think that'd be great for just because I'm always looking for good material to kind of show to people who are new to the language, or just things that are cool, things that you find. So yeah, that's it for today. I hope you guys have a great evening. Now I'm going to stop broadcasting.